lecture 37, and we were discussing mixture fraction, and at the end of the class I got some questions on mixture fraction, and rather than answering those questions directly, I will try to take an example which will illustrate the concept. So let us consider a non-premixed ethane air flame. So this is C2H6 and air flame, and some species are measured in that flame. Those species are C2H6, CO, CO2, H2, H2O, nitrogen, oxygen, and OH. These are measured. So how do we write the mixture fraction? We write mixture fraction Z as MC plus MH divided by M of mixture, and that is So if you look at the notation, you will get an idea of what we are trying to do. So it has now 7 constituent terms. So what is MC bar C2H6? What do you think it is? Mass of carbon in C2H6 divided by mass of mixture, and you will see that there is also a mass of hydrogen in C2H6 divided by mass of mixture. Similarly, mass of carbon in CO and mass of hydrogen in CO of course will not appear, so that is gone. Mass of carbon in CO2 will appear, mass of hydrogen in CO2 will not appear. Mass of hydrogen in H2 will appear, mass of carbon in H2 will of course not appear. So like that, you can see that based on the species that we have, this tells you that if you add these terms, you should be able to get mass of carbon plus mass of hydrogen divided by mass of mixture. Okay, so does this seem reasonable? Okay, so why are we writing mass of carbon plus mass of hydrogen divided by mass of mixture? Because that's how we wrote mixture fraction in the last class. So this is one way of looking at mixture fraction, as I said. This is mass of material which is originating in the fuel stream divided by the mass of mixture. So if it is a hydrocarbon fuel, like in this example, ethane, so then fuel stuff will actually mean that carbon or hydrogen. So we wrote kg of fuel stuff divided by kg of mixture, which is the same as writing mass of material originating in the fuel stream divided by the mass of mixture. So that is why here we want to account for the mass of carbon and the mass of hydrogen through various species which have been produced. So carbon is there in ethane, carbon is also there in carbon dioxide, hydrogen is there in ethane, but hydrogen is also there in OH radical. So if you put everything together, then you get the mixture fraction. Okay. Now this can be further written, of course. I will just show you how to write one of the terms, and then you will be clear how to write other terms. For example, McC2H6 divided by M mixture is one term that we had. So we can write that as this, which is what's this one? YC2H6, right? And what about this? correct? W for molecular weight. So, this is the mass which is present in this much. So, for this we are writing this. Is that okay? C2H is roughly, it has a molecular weight of 30, and out of that 24 is because of carbon. So, this number is more like 24 divided by 30. And there are other terms, of course. I just wrote the first term. There are of course other terms which can be written similarly. That is what in fact we had done in the last class. So, let us go back to what we had done in the last class, and this is what we wrote for mixture fraction. Mass of material coming from the fuel stream divided by mass of mixture, that I wrote as kg of fuel stuff. Now we understand what this is, right? Carbon and hydrogen, for example, if it is a hydrocarbon fuel. If there is something else, if there is, let us say, sulfur in the fuel or something, so that also has to be accounted for. But in the ethane example, it was only carbon and hydrogen. So, it is kg of fuel stuff divided by kg of mixture, and that we wrote as a sum of 3 terms, because in the chemical system that we thought of, we had 3 species, again fuel, oxidizer and products. Accordingly, we wrote these 3 terms. But at the end of the class, I understood that there was a difficulty in the sense that you felt that these 3 terms were actually repeating something. Okay. So, you thought that first term is kg of fuel stuff divided by kg of mixture, cancelling these 2. Second term is also kg of fuel stuff divided by kg of mixture, and third term is also the same thing. So, it was getting triplicated, wasn't it? That was the question. So, do we have an answer now? Okay, what is the answer?
They are not repeated. They are only a part of it.
Yeah, so actually what I was saying that time, and I think we did not have time to close the discussion, is that I said that this is kg of fuel stuff in fuel. Okay. So, that I think by now should be clear. You had a question.
Exactly, this
yeah.
is what I wanted to.
Yeah.
It's a part of fuel only, it's a part of mixture of the fuel which is coming. It is an integrated part of the fuel, and in the fuel itself it is there.
Yeah, so we are talking about when we say kg of fuel stuff, think about the ethane example, it is giving carbon and hydrogen. So, this is this term, the one which I am pointing to, this term, okay, this term is mass of carbon and hydrogen per unit mass of fuel, which is in the fuel. Okay, so that will turn out to be 1. That will turn out to be 1. Now, let us take another case. This is kg of fuel stuff in oxidizer, which is 0. Now, what about kg of fuel stuff in products, which was the third term? Okay. This will be, in this example that we wrote, this will be 1 out of S plus 1, because the reaction was, yeah, I think we can look at the reaction. Yeah, we were saying that this is 1 kg of fuel plus S kg of oxygen giving you S plus 1 kg of products. So, kg of fuel stuff here is 1, here it is 0, no sorry, here it is 1, here it is 0, and here it is 1 again, right. So, if you add all these things, then you get the total kg of fuel stuff. So, that means the carbon and hydrogen are coming with the fuel, they are partly in the fuel now, but they are partly also in the products. So, what we are saying is that we, in any zone of the flame, if you take a small sample, the sample will have fuel, and it can also have oxidizer, it can also have products. Maybe something is 0 there by chance, but in general these 3 things can be present. So, this contains some fuel stuff, this does not actually contain fuel stuff, but this will contain fuel stuff. So, if we are talking about the mixture fraction, then it is kg of fuel stuff divided by kg of mixture. So, the fuel stuff is actually getting distributed in the fuel and in the products. So, that is why we need the summation of these two terms, and we wrote last time as this. So, this turned out to be here fuel was fuel mass fraction has to be multiplied by 1, here product mass fraction has to be multiplied by 1 over S plus 1 to give you the entire mixture fraction, because the fuel stuff is here, the fuel stuff is also here. So, this is fuel stuff in fuel, this is fuel stuff in products. Okay, so that's how we got this.
It's fuel stuff only in the fuel, or the fuel stuff in the stream which is coming. Like stream may be having something other than the fuel also.
Yes. So, this is kg of fuel stuff which is coming from in the fuel stream. So, that is the only thing that we are accounting for. Okay, it may have inerts, but we are talking about kg of fuel stuff like carbon or hydrogen or something else, something which is burning. And this mixture fraction definition that we have given, this is actually for one fuel stream and one oxidizer stream. Okay, so we are actually done with non-premixed flames, laminar non-premixed flames. Just one thing I wanted to show you. I think in my estimate we will not be able to discuss turbulent non-premixed flames, but I will just want to share one plot with you. This is flame length, this says height, but basically flame length for a jet flame as a function of flow velocity, jet nozzle velocity. So, flame length as a function of jet nozzle velocity. So, we were considering laminar situation. So, the laminar situation, the height for a given nozzle is just proportional to velocity. So, you will see a linear increase. So, the height was proportional to QF. We are talking about a given nozzle, a particular nozzle. So, it will be, the height will be proportional to the flow velocity. Okay. So, it goes linearly. Of course, when the flow velocity is 0, there is no height. So, it starts from 0. So, this is a straight line from 0. Now, if you keep on increasing flow velocity, the flow will become turbulent, okay, through a transition region. So, there is a transition region. So, there is a laminar region, there is a transition region, then there is a turbulent region. So, what happens is, and I am actually not really explaining this, analyzing this, but this will just accept as some information which we can use. In the transition region, the flame length actually goes up a little bit and then it drops like this. And after the flame becomes turbulent, the flame length does not really change much. Alright, so that is one important information. You can see from the nature of the contours that have been drawn for these flames that these are turbulent flames, whereas these are smooth flames, so these are laminar flames. So, these are laminar flames and these are turbulent flames. In between something happens which is transition region. So, turbulent flames tend to give you same sort of height even if you increase the flow rate. Okay, we are talking about a jet flame coming out of a nozzle. And another noticeable point is that the height of this turbulent flame is actually somewhat smaller than the laminar flame. Okay. So, this information is good to know, but unfortunately we will not be able to analyze this, just do not have time. Okay. Now, what we will do is we will discuss a new topic pertaining to liquid fuel combustion. And if you recollect what we discussed at the beginning of the semester, you can have nozzles, and from that we can generate sprays of fuel, liquid fuel, and that can be in an oxidizing environment, and then that can burn. So, liquid fuels are often burnt by us engineers by producing sprays. So, it is typically spray combustion. An example of this can be in diesel engines, and of course in gas turbine. Gas turbines can use liquid fuel. Gas turbines, if they use liquid fuel, then they will also have to produce this kind of a spray and then burn it. Apart from gas turbines and diesel engines, there are also furnaces and other combustors where spray combustion is used. So that's how liquid fuel is typically burnt. Now, why do you want to break it into a spray? Because unless you break it into a spray, your combustion times will be large. In fact, in the spray you will have droplets, and if the droplet sizes are large, then the combustion time is also going to be higher. So what I am saying is, in the spray, if you have a droplet which is big, it will take a longer time, and if you have a smaller droplet, it will of course have a smaller time. And I think I mentioned this some time back, that for example in a diesel engine, you have limited time for combustion, isn't it? So you have air which has been compressed, and then you have sprayed it, and then you are because of the high pressure, it's going to get ignited and burned, but you want that process to be over quickly so that you can get the hot gases which will push the piston down. That is the objective. The objective is actually not to do combustion as such. Combustion is not the primary objective. Through combustion, we are achieving this objective of producing these hot gases which will push the piston down and thereby run the crankshaft. That is the idea. And we have limited time for the combustion process. Since we have limited time, we have to burn the fuel quickly, and you can burn the fuel quickly if your droplet size is smaller. Okay. So when you produce the spray, make sure that you produce a fine spray. If the droplet sizes are large, like millimeter size, then you will have problems. Now, in the analysis that we will do in the next few lectures that we have, we will not be able to really analyze spray combustion, again because of the interest of time. And we will try to understand droplet combustion, because that is easier and it actually has features of spray combustion, so we can understand it to some extent. We can do some analysis, we can do some theory for droplet combustion. Spray combustion would have taken much longer. Now, if you have a droplet, then what is the easiest problem that we can solve? The easiest problem will be to have a droplet which is stationary and which is in an infinite oxidizer field. Okay. Infinite and quiescent oxidizer field. This is the radial coordinate. So as always in a course like this, we are trying to catch the simplest possible problem. So we are trying to think of which droplet problem is the easiest. So if you have a stationary droplet which is not moving and which is in an infinite oxidizer field where the oxidizer is also not moving, there is no flow, then the problem will be easier. Well, this much we understand. Understanding meaning we suspect that that's what is going to happen, because if you introduce flow in the air surrounding the droplet, that's additional complication. If you have the droplet move, then that is also additional complication. So keep the droplet stationary, give an infinite supply of oxidizer, so the oxidizer concentration around the droplet, some distance away from the droplet, can be taken to be constant. We are not allowing the air to move. Plus we can also say that there is no effect of gravity. Okay, because if there is gravity, we suspect that there will be a flow pattern set up. Okay, you will expect some flame to form like this if there is gravity. I think you already have that instinct because you've seen candle flame, how it assumes the kind of shape that has. So if you do not have gravity, then a flame around a droplet will be like this. So that will be easier because that will be symmetric. So we have these sort of simplifications. Now, before we go to the droplet combustion problem, we will first think about, okay, we are doing a simple problem, no doubt, we are doing the simplest possible, but how different is it from the actual problem? Then the actual problem of spray combustion, these droplets are moving because there is a pressure difference. This is high pressure here, lower pressure here. So this droplets, there is a droplet stream flowing out of the nozzle. So the droplets are moving. So that's one difference. Droplet is not stationary. If you think about an engine kind of situation, then the piston is also moving, and there is a pressure change also. Then there is some flow pattern in the cylinder, which also we are ignoring in droplet combustion, single droplet combustion. This is single isolated droplet. Whereas these droplets are not isolated. They are not of the same size. There are multiple droplets, and these droplets are of different sizes. Because if you are producing a spray, it is actually very hard to make sure that all droplets are of the same size. It is nearly impossible. So if you have all droplets of the same size, it is called a monodisperse spray. Very hard to get. So actual sprays are typically polydisperse, in the sense that it will have various kinds of diameters. They will have a droplet diameter distribution. So different diameters, that means different sizes of droplets. These droplets are moving, and they are not moving with the same velocity. They're moving with different velocities. Air around here is also moving, and since there are multiple droplets, these droplets, the droplet here and the droplet here and the droplet here, they can compete with one another in terms of consuming oxygen. They will need oxygen for combustion, but they are all nearby, so they are competing for oxygen with each other. And there is some interference also there, because they are close by. The large number of droplets close by, so there is interference also. So the droplets are not isolated either. Fine. But maybe single isolated droplet is still something which we can study if the spray is kind of dilute, the less number of droplets, and then maybe they are closer to being isolated. Still not isolated, but closer to being isolated. So that is why we are studying single isolated droplet. And for droplets, we can of course think about an evaporation problem and also a combustion problem. So again, if you choose the easier problem, the first problem we would like to solve is an evaporation problem. Okay. And in a combustion situation, of course, evaporation will also happen, because suppose this blue sphere is your droplet and this one is your flame, then how does the droplet burn? Of course, the flame is at a higher temperature, and flame transfers heat to the droplet, and the droplet evaporates. So there will be definitely evaporation of the liquid from the droplet towards the flame, correct. So evaporation will happen. So even in a combustion process, even though we are saying droplet combustion, it includes droplet evaporation. So if you think about it, if you think about what happens in a flame, of course we will have fuel moving towards the flame, and we suspect that oxygen from the air will move towards the flame also from outside. Okay. So fuel goes towards the flame, and oxygen also comes towards the flame, right. So this will be non-premixed combustion, diffusion combustion. So that this is the overall picture of single isolated droplet combustion. Now first we think that it will be good to understand the droplet evaporation problem, because droplet evaporation is part of droplet combustion process. Droplet evaporation has to happen. When we are burning a liquid fuel like this, first the fuel vapor is produced, and then the fuel vapor meets the oxidizer, then combustion takes place. Okay, it is not like liquid burns as liquid evaporates first, because the oxidizer is present in the gaseous phase. So it is easier if the fuel also comes to the gaseous phase. So then they are in the same phase, and a homogeneous reaction takes place. Homogeneous means all the reactants are in the same phase. Okay. What is a heterogeneous reaction? If let us say oxygen is attacked by oxygen attacks a carbon particle. Let us say we were discussing soot particle in the last class. Soot burns, soot gets oxidized in the air. So, then the solid carbon particle is getting attacked by oxygen of air. So, that reaction is not a homogeneous reaction, that is a heterogeneous reaction. But here it is a homogeneous reaction which will take place when the fuel vapor will meet the oxygen at the flame, right. So, we understand this is non-premixed combustion. First, let us understand liquid droplet evaporation problem. What are we interested in? So, forget combustion for the time being. Suppose you have a single isolated droplet in some atmosphere and it will evaporate. What will you be interested in as an engineer? What question would you like to tackle? What question, for which question you would like to find an answer? So, rate of evaporation. So, rate of evaporation is of primary interest to you. Even if you have water droplet, let us say not a fuel droplet, you like to know how fast it will evaporate. So, evaporation rate, and depending on the evaporation rate, each droplet will have a lifetime. That means, it starts with a certain size, let us say 1 millimeter diameter droplet. It will take some seconds or maybe a fraction of a second to evaporate completely. That is called a droplet lifetime. So, we are interested in droplet evaporation rate and droplet lifetime. Actually, if you get the evaporation rate, maybe you can reach the droplet lifetime also. The other things which we can be interested can be interesting is, and related in fact, is droplet radius as a function of time. Of course, it will depend on the evaporation rate, isn't it? So, droplet radius is a function of time. Actually, we will call it RS. So, if this is the droplet, we call this RS. We will also like to know temperature distribution. Now, this droplet, let us say it is a colder droplet kept in a hot environment, then there will be temperature variations. So, there will be temperature as a function of R, okay, and in fact also with time, but at a given instant of time, what is temperature as a function of radius, and also species distributions. Species mass fractions as a function of R. So, I will not do this problem fully, but I will do this problem to some extent and give you a flavor of this, so that it becomes easier for us to do the droplet combustion problem. Now, some assumptions which are made for the droplet evaporation problem. One assumption is that, as I told you, the droplet is in a quiescent infinite oxidizer field. So, quiescent infinite oxidizer field, then the evaporation process is assumed to be quasi steady. Now, this is an assumption in which we drop the time terms, the transient terms in the conservation equations. Okay, so, we assume as if what we are writing at any given point of time can be obtained by neglecting the transient term in the equations. So, that is why it is called a quasi steady solution. Quasi steady solution means, if you take the energy equation or if you take the fuel mass fraction equation, they will have del T term, okay, del temperature, del time, or del YF del time, these sort of terms. But we will neglect those, and if we neglect those, then temperature becomes a function of radius and fuel mass fraction also becomes a function of radius only. Now, are these correct? If we solve these and get temperature as a function of r only and fuel mass fraction as a function of r only, it so happens that this is not a bad assumption. Okay. So, this is roughly the profiles that you get will be roughly okay. So, this assumption is called a quasi steady assumption, and some other assumptions is that the temperature of the droplet is taken to be the boiling point temperature. Now, this is especially true because we have hot surroundings in combustion kind of situations. So, the droplet will get heated to its boiling point temperature or very close to the boiling point temperature. If you think about this modeling, let us say evaporation of a water droplet in this room or slightly higher temperature than air normal temperature, then that may not reach the boiling point temperature. But we are talking about hot surroundings, so the droplet temperature will reach close to the boiling point temperature. We also assume alpha equal to d, so unity which number? Lewis number. Unity Lewis number, all thermophysical properties to be constant. Again, trying to keep things as simple as possible. The fuel is a single component liquid. With zero solubility for gases. So, these are some of the assumptions, and I will try to write the mass conservation equation and also the energy conservation equation. And then from there we will be able to learn something about how to get the droplet lifetime. Again, remember that we are looking at the droplet evaporation rate and thereby get the droplet lifetime. This is roughly what our plan is. We are interested in the droplet evaporation rate. Now, how do we write mass conservation? So, that is easy. You have to write mass conservation equation in spherical coordinates. R is at the center, R equal to 0 is at the center of the droplet. So, we can write del rho del T plus so this is rho r squared, yeah. And this we set equal to 0 because this is an assumption that we are making. We are saying that this is quasi steady. And this is 0, del theta and del phi to be 0 because we are taking a spherically symmetric situation. So, that is okay because that is the simplest problem. So, that means 1 over r squared this is 0. Where did I get this from? This is mass conservation in spherical coordinates. So, if you look up standard textbooks, this should have. All right. In fact, I mentioned one book by Kenneth Kuo some time back in connection with detonation. So, for example, that has, and several other books will have. This is mass conservation in spherical coordinate system, and mass is always conserved, and whether it's combustion, non-combustion doesn't matter. So, even other fluid mechanics books and heat appendix of the heat transfer books, they will all have this. So, spherically symmetric. So, these two terms will go, and we are assuming quasi steady. So, we are taking this to be 0, and then this becomes our conservation equation. We can do a slight trick by writing 4 pi here, 4 pi r square rho V r, and that means del r of, this is m dot, this we call an m dot equal to 0. So, m dot is constant. M dot is constant, and m dot is the same as m dot f, which is rho V r 4 pi r squared. All right. So, let us see what is happening. Mass conservation. This is mass conservation equation, and you can see some velocities, right. You can actually, okay, slight correction here, this is V, and this is V also, this is V phi, and this is V r, this is the only velocity which is mattering. So, this is a velocity, V r is a velocity. So, that means there is a velocity in the radial direction, correct? There is a velocity in the radial direction. There is no other velocity. There is no V theta, there is no V phi. Now, if you think about it, this is kind of interesting, because we said that the droplet is stationary, we said that the ambient is also stationary, isn't it? There is no flow in the ambient, there is no flow, no movement of the droplet. But if you write this mass conservation equation, you see that there is some flow, there is a V r. Okay. This, how does this V r come into picture? Yeah, so it is evaporating, so this is the flow. So, this is generating its flow. It is not like you have given it a flow. So, this is happening, right. So, this is mass conservation. Now, we will write the energy equation also. Energy equation in the Schwab-Zeldovich form. Now, this was done some time back when we were doing premixed flames. You remember Schwab-Zeldovich, and at least the names, isn't it? So, this was done some time back when we were doing premixed flames. So, we did this planar analysis of a premixed flame to get expression for laminar burning velocity. So, that time we used the Schwab-Zeldovich formulation for the energy equation. Now, here of course, we cannot use the planar form, we will use a spherical coordinate form. This is a spherical coordinate form, and where can you look this up? Chapter 7 of turns, correct? I think you have already done that once when doing premixed flame. But we are writing the spherical coordinate form. So, that equation is All right, something like this. Just go to the chapter 7 of the book and pick up this equation. That's all. I'm not asking you to derive this, even though we derived a similar equation for planar flame. Now, once we have picked this equation up, let's see what these different terms are for. What is this term for? This must be, yeah, so this must be the source term, isn't it? So it has an m dot I triple prime. So that's the production rate of the ith species associated with enthalpy. So this must be the chemical energy source term, right? And what are these two terms for? This term, very easy to see, it has a d. So this must be diffusion, diffusion of heat, but it has the capital D. It's not a mass conservation, mass species mass transfer equation, but it still has D, because somewhere we must have used Lewis number, isn't it? Schwab-Zeldovich homogenization, we must have used Lewis number equal to 1 and things like that. And so this is heat diffusion, and this one is advection of heat, isn't it? Because this has got the velocity term. So this is a, call it convection or advection. So this is a convection term, this is a diffusion term, and then there is a reaction term. Of course, the good news here is that you can actually neglect this one, because we are talking about droplet evaporation. There is no reaction taking place. This problem just is droplet evaporating, that is all. It is not doing anything, it is not reacting, the fuel vapor is not reacting. So this goes, this can go. And remember also, we said that we have taken all the thermophysical properties to be constant. So this Cp will be constant, so this will become integral Cp dt will become just Cp into T. So we can do these things, and it's actually not hard to show. So one or two steps. So ddr, this becomes ddr of r squared dt dr. Now K now is the thermal conductivity. So we've gone back to terms, so now it's no longer lambda. Okay, so this is K, this is thermal conductivity. Cpg is Cp, Cp of gas. So that's why it's Cpg. Remember that now we have liquid as well as vapor, liquid as gas, liquid phase, gas phase. So we have to make a distinction. So we are writing this to be Cpg here. K is actually thermal conductivity of the gas phase. So we have this equation, and this equation actually can be solved, right? Can be solved subjected to some boundary conditions. So there are easy boundary conditions actually. We can use these two boundary conditions. What will these two be? Evaporating droplet, very far from the droplet we should have T infinity, and at r equal to Rs, Rs is the droplet surface, T boiling, okay. So this is T boil. So one can solve this, and one can get temperature as a function of the radius, correct. So it's pretty easy. M dot is a constant, this M dot is a constant. So when you integrate, it's easy because m dot is already shown to be a constant. We did the mass conservation, m dot is constant. Constant means what? You go from one r to another r, m dot is the same. Okay. We have shown this just a few minutes back. We have shown this that m dot is rho Vr 4 pi r squared, which is a constant. So you go from one radius to another, m dot doesn't change. Same m dot. The flux of course will keep on changing. Flux will decreasing as you go to higher radii. So this m dot is constant, no problem. So it makes it easier for us to integrate. We will integrate this, we can get temperature as a function of r. I am not doing the details. So we can get T as a function of r. Now, what to do next? We are interested in getting the droplet evaporation rate and thereby to get the droplet lifetime. So, how do we get that? I mean, if we want to understand that, if we want to get that, we have to understand how a droplet evaporates. How does it get the energy to evaporate? It needs some energy, it will absorb some energy and then it will evaporate, isn't it? So, how will that come from? Where will that come from? So, you can have this droplet here. And let us use a red color to show high temperature, let us say. So, this is the radial distance marked with R. So, red means is high temperature here, blue means is low temperature here. A droplet is at the boiling point temperature. Boiling point temperature is far less than the flame temperature. Flame temperature is of the order of 2000 Kelvin maybe, and the droplet temperature is boiling point temperature. So, let us say for heptane, boiling point temperature is I think 98 degrees. So, it is a much lower temperature, 98 degree Celsius. Okay. So, here there is some temperature here and then the temperature has to go up, right, in this region, and then the temperature will drop down if we show it as a function of the radial distance. That is what we expect, because at the flame the temperature will be higher, and we already have some diffusion flame background. So, we know that there is fuel going this way and there is oxidizer coming this way, they will meet here and they will react. They will produce the maximum temperature where they meet and react. If the reaction rate is very high, then this zone which I have marked with red will be thin, and otherwise the reaction, this thickness will be higher. But this is a combustion situation, right? This is a combustion situation. So, this much we know from our combustion understanding, but here we are talking about droplet evaporation. So, in the absence of a flame. So, in the absence of a flame, what did we say? That so in the combustion situation, it is easy to understand. This is high temperature here, this is low temperature here. So, there will be some temperature gradient, strong temperature gradient. But here also, this is at the boiling point temperature and it has been kept, let us say, at a relatively higher temperature. Then we expect that the temperature will be higher some distance away, maybe this is T infinity, and towards the droplet it will tend to come down, right. So, this will establish a temperature gradient, because this is after all at the boiling point temperature. This is not very high. No. T infinity can be very high. T infinity can be, you can think of T infinity as like this. T infinity can be, let us say, the temperature of the gases inside the furnace. So, there is a spray going in, there is a droplet going in which is cold and the furnace temperature is high. So, it will raise this. Okay, so, this is one way of raising the temperature. We are thinking about a situation when there is a high temperature environment and the droplet in fact reaches close to boiling point temperature. There can be other way also, but before combustion, suppose you give a spark and then flame is getting formed, then also it will get heated, but we will not go to that because that is closer to a combustion situation. So, there will be a temperature gradient, there will be a temperature gradient which will help in help this to evaporate. So, what is happening is there is some enthalpy which is going to the droplet surface, some heat is getting added and some enthalpy is moving out of the droplet surface. Okay. So, this is, let us mark this one, this is m dot H liquid. So, there is some m dot of liquid going to the surface carrying enthalpy H liquid, and there is some m dot going out of this surface carrying enthalpy H vapor, and there is a q dot. Who is supplying that q dot? Q dot is being supplied by this temperature gradient. And what is the mechanism of this transfer of heat? Conduction, convection, radiation, which one? This is conduction. Okay. Radiation will primarily neglect. If it is a thin flame, then the radiation from the flame is not very high. So, this is by conduction. So, this q dot is by conduction. This temperature gradient gives you q conduction. So, q dot conduction plus m dot H liquid is equal to m dot H vapor. Just looking at this picture. So, q dot conduction is m dot H vapor minus H liquid, which is m dot times HFG. So, q dot conduction is in fact 4 pi r s squared kg dt dr at r equal to r s. Where is q dot conduction? Let us see. Is this okay? This is heat going into the droplet surface. So, we are doing a surface energy balance. Heat going to droplet surface by conduction. So, add the things, add the arrows which are going in the same direction, we are meeting. So, these two arrows are directed towards the surface. So, q dot conduction plus m dot H liquid will be together, that is equal to m dot into H vapor, fine. So, this tells you that q dot conduction is m dot into HFG, this much is fine. Okay. Now, what do we say about this q dot? We said that this q dot is by conduction, there is not much effect of radiation. Typically, that is correct, unless there is like some soot. So, unless there is significant soot in the flame, it will not be so much because of radiation. So, this is more by conduction. So, if it is by conduction, is it okay to write this? Okay. So, this is minus k into area into dt dr evaluated at r equal to rs. So, this is Fourier's law. Why do not we have the minus sign? Yeah, so we are looking at this one. We are not looking at the outward flux. We are looking at the inward flow of heat, not the outward flow. If we wrote the flow of heat in the positive r direction, then it would have been minus k a dt dr. Okay. Where are we evaluating it? We are evaluating it at r equal to rs, at the droplet surface. Now, we have to remember that this is dt dr based on the gas phase, right. It is not a dt dr which is evaluated from the liquid phase. Actually, liquid is taken to be at a uniform temperature. Liquid can also have temperature gradient. I mean, it is possible, no? If you think about it, it is possible that the center of the droplet is at a lower temperature and the surface of the droplet is at a higher temperature, it's possible. But we are saying that that's not happening. The entire droplet is almost at TB. So we could have done that, but that would have been more sophistication in the model, which we don't need because that doesn't make a major change. Okay, so we'll close, and I think we'll have to close now, but the point is that from here we are to see how to get the droplet evaporation rate. So how do we get m dot using what we know from here? So that is where we'll start tomorrow. Thank you.